Okay, ladies and gentlemen, hello and welcome back once again. Thank you so much for your time and attention. And we're going to talk about database and database survival. This is a special research webcast today with Barry Morris of NuoDB. We're very happy to have Barry on the show today. He's frankly a visionary in this space. And so we're going to be talking about what those folks are doing and what this whole concept of HTAP is all about, hybrid transactional analytical database. It's not completely new, but it's certainly taking off these days, and we're going to talk about what that means, what the space really is, why we got here, and what it means going forward. So I'm just going to share a few slides from Dr. Bloor's presentation of a couple weeks ago, database disruption. You know, I actually remember, and Barry, maybe you can comment on this in the Q&A section at the end of the show. I remember back in 2005, the year of our Lord, did an interview with Michael Stonebreaker, of course, the database visionary from years and years ago. And I remember he was pushing Vertica back then, and he had this whole pitch around one size does not fit all. And he said that what's happened in the marketplace, and he had some interesting theories on this, was that the relational database dominated and was filling all the gaps and all the voids and serving all things to all people. And his point was that the time had come for that to not be the case anymore. His argument was that there are use cases where a traditional relational database model is simply not going to be performant enough to do what end users want it to do. And obviously, the cloud had a lot to do with that, but just use cases at large organizations who wanted to do heavy analysis on data. His argument back then, of course, was that a column-oriented database would be much more purpose-built for those kinds of solutions for a variety of reasons, one of which simply being that columns compress a lot easier than rows do, simply because they have all the same kind of data in them. And when push comes to shove, let's face it, everything in the database world is going to be about performance. You want your database to perform the way it needs to in order to solve your business needs. And I think that dating back to 2005 and just before, we really started to see that trend evolve where organizations realized they wanted to analyze their data. They realized that traditional approaches were not quite delivering what they wanted. And this is back when I worked at the Data Warehousing Institute. So, of course, the whole data warehouse evolved out of a need to do analysis on data. People realized they couldn't be querying these ERP solutions. They had to pull that data out, load it into a data warehouse, then do their analysis on that environment. Well, you know, what goes around comes around, right? In a way, we're kind of going back to the old way of doing things now with these hybrid databases and with some other solutions on the market. You know, specifically, I keep thinking about S/4HANA, SAP, and their whole interesting approach. So things are changing, but boy, was Dr. Stonebreaker correct. He said that we were in the middle of a transformation. That was really the beginning of the evolution of this whole movement around NoSQL, or not only SQL, or new SQL, as some folks like to call it. So a lot of the innovation came from the big web giants. Let's talk just for a second here about data governance. And I'm really just trying to tee up Barry for his presentation. But I mentioned data governance because of a couple things. One, we've got this GDPR coming down the pike, the Global Data Protection Regulation out of the EU, and this whole concept of right to be forgotten, which I find absolutely fascinating. I mean, my very candid, cynical perspective is that it's an unachievable goal, quite frankly, and it's largely just going to be used as a cudgel by the EU to cow companies into line. And there are good reasons for this. You want to have some privacy. Certainly in the EU, they're very respectful of that. Not so much in the United States. I think we all understand that. There are cookies everywhere. People are tracking your every move. We just kind of accept that here. But that's just one reason why data governance is important. Of course, hacking, just knowing what's going on. We keep hearing about all these hacks everywhere. So security, compliance, all sorts of issues come into play with respect to governance. You have to keep that in mind with your database, obviously. So just a couple slides here from Robin's presentation. You can see some information about SQL. You know, it's interesting. We had this movement away from SQL. That's where you got the NoSQL from. And typically what happened is the innovators, like you can consider what came out of Facebook, what has come out of some of these other web giants, what did they want to do? They wanted higher performance for a certain part of the database stack, essentially for certain use cases. So typically, when we talk about ACID compliance, what we gave up was consistency. And you had this movement toward what's called eventual consistency. And there was even some interesting stuff that came out of Kafka where before Confluent spun out as a company and hardened Kafka, back when it was just the engine that drove LinkedIn, you didn't even have eventual consistency. You could actually lose transactions because it didn't really matter. And this kind of speaks to the whole heart of why things are changing in the database space. It's all about the business and the business needs. What are we trying to accomplish? What do we need to achieve? How can we get that performance we need effectively? And the answer is pretty simple. What you do is you give certain things up. So the NoSQL movement came around. Everybody got excited about that. There are lots of NoSQL databases. In fact, I'll throw up a slide here with just some basic information about that. So a lot of excitement around NoSQL because of the performance, but then what happened? All the NoSQL vendors started strapping SQL engines onto their NoSQL database, right? Because people realized for a variety of reasons SQL is here to stay. SQL is the standard. SQL is very important for a variety of reasons, one of which because lots of people use SQL, lots of people know SQL. You know, one of the challenges that we have, and Barry and I were chatting about this before we hit the record button, in the whole big data space is that for the major players, your Cloudera, Hortonworks, MapR, the reality on the ground is that when push comes to shove, you need a lot of expertise in-house or through some consulting firms to stand these solutions up. Well, guess what skill set is all over the place in just about every country on the planet? SQL. Lots of people know SQL. So if you adhere to that, if you respect the fact that SQL is the standard, you're going to understand why SQL is coming back with a vengeance these days. So lots of different database types. We've talked about horses for courses, as my old buddy Jim Erickson used to say on DM radio. And these days you really have to think about your use case. What is your business model? What are you going to need? And we talked again before the show about the whole concept of scalability and elasticity. I think this is one of the major drivers for innovation, and it's why NuoDB is doing pretty well these days, because they saw this years ago as they began their journey, and then they took a pivot a few years ago, I think, when they realized exactly the magnitude of what was coming down the pike. If you think about, especially if you're in the marketing world, think about when something goes viral. I saw this just the other day with a promotion around an article that I had written on LinkedIn, and doing some promotion, according to Bitly, it went viral. It went from 50 hits to 5,000 hits in like a matter of minutes. Now, personally, I think probably there were some bots in there. There's something weird that happened. You never know, and this is one of the downsides of the modern web-enabled world, is that you can't really get behind a lot of these engines to understand what's happening. But the point is it went viral. Now, imagine if you are some brick-and-mortar company who is selling widgets, but you're now selling them online. And once that goes viral, if you do not have the ability to scale out to essentially leverage elasticity in your infrastructure, you're going to have a lot of unhappy prospects. You're going to lose that opportunity. I think that's the key. The opportunity cost is massive if you're not able to scale out as needed, and that something can go viral at any point in time. So this is why distributed databases are such an attractive option these days for companies in the new modern web-enabled world. If you have the elasticity and you have ACID compliance, if you have durability and elasticity all in one, you're positioned for success. And with that, I'm going to position Barry Morris of NuoDB to share with us what he has. And Barry, I've just now given you the keys to the WebEx. Take it away and show us what you got.
Well, thanks very much, Eric, and hello to everybody. So I just want to basically take you through some background, and we'll have some chat about it afterwards and welcome your questions. The core of what I have to say really is about exactly Eric's comments on elasticity, and so we need to jump into that. The really starts with, and you have in front of you, I think here, sort of depiction of the database decision maker, and what's been the case now for some years has been this person having to decide whether or not they care about elasticity more than they care about strong data guarantees and powerful server-side processing. And in general, the answer has been that the former is where people have gone. And so hence a lot of the conversation about NoSQL, which a lot of the time has been as much about no transactions, people have sort of taken the right-hand path and said, okay, we're going to have to give up on some of the things that we've been used to over a period of some decades in order to get the things that we really want on the right-hand road. What are they giving up? Well, Oracle's a very powerful system, so is SQL Server and other relational databases. These are very high-performance systems, very reliable systems, very secure systems, give you lots of guarantees about the data. And there are things that is how we run the world, really. There's a $40 billion database market, of which almost all of it is SQL and based on those kinds of technologies. And so that's a big thing for us to be giving up. And really, I wanted to talk about these two roads and then talk about where we're going with it. Let me see. So basically, the question of why elasticity, and some of this you'll be quite used to, but imagine what you can do with an elastic database. It starts with, you're not going fast enough, add a node. That's not what you can do with a traditional database, of course. You can't just add a node to Oracle or to SQL Server or something. Elastic database is a database. You're not going fast enough, you add a node. Same thing for latency. Latency is actually much more important than people realize when it comes to databases. People don't like waiting for web pages. Often when your machine starts getting overloaded, latency is the first thing that takes a hit. Guess what the answer is? Add a node. The same thing if you've got too much data. Your database is getting too big. What do you need to do about it? You need to split it into multiple stores. If you want to split it into multiple stores, Elastic database allows you to just add a node. Same thing for users. I think you're getting the pattern. It's Black Friday or whatever it is. You've got several million more users. What are you going to do? Elasticity is all about just adding nodes. And the same is true for redundancy. If your system needs to be resilient to the loss of a machine or the loss of a disk drive or whatever, the simple answer in an Elastic database is add a node. And that's really the point, is that add a node is the answer to almost any question when you're talking about elasticity. Same with new workloads. Here's an example of somebody who wanted to come in and do some analytics. Maybe it's a monthly report or whatever it is. And you don't want to run that on your existing resources because they're running transactional workloads. No problem. Add a node. Add a big node if you want. Add a node with a terabyte of DRAM and run your reports there and switch it off when you're done. That's what elasticity is about. Equally, you can delete nodes. Most database servers, as you know, run at like 5 or 10% utilization of the server because they're provisioned for the 500-year flood. And in an Elastic database system, you don't have to worry about that. You can shut down nodes at any time. You don't lose any data. You don't lose any transactions. And users don't see any loss of service. Even upgrades. You want to do a rolling upgrade, you want to upgrade machines or upgrade operating systems, upgrade the database software itself, that's no problem. Just add some new nodes and delete the old nodes and keep going. So elasticity is much more than just capacity. In fact, in certain Elastic databases, and we'll talk about this if we have a moment later, you can add your nodes wherever you want. So if you need low latency in London and in Tokyo and in New York at the same time, just add your nodes in those data centers and keep going. You obviously can't do that with a single server database system. There are a bunch of other things, automated management, hooking into Kubernetes and microservices and all those kinds of things. These are all part of what an Elastic system can do that a dedicated server system can't. But the bottom line is dollars. And now what we're talking about is systems that are on virtual infrastructure. There are systems where you're paying by the drink. There are systems where you're moving from capital costs to operating expenses. And so elasticity, when you go back to the original question, of course you want elasticity. That one's not negotiable. The questions are really all about the other two pieces, and so let's jump into that. Sometimes when I hear people talk about ACID transactions, you get this kind of strange comment that, well, you don't really need ACID transactions except for very, very few workloads. And that kind of misses the point. ACID transactions are not about that. They're about the fact that they change a lot about how we build applications. For one thing, guarantees of durability. And you definitely want that. What this means is if you tell the database system to store something, it's stored. And, absent a meteor blowing up planet Earth, that data is there. That's something that you want. I've heard people say, well, if it was only a picture of my goldfish or my poodle on Facebook. But even then, you'd rather that it stays there than it doesn't. So durability is a great guarantee to have, and you definitely want it if you can have it. The same is true of consistency. You want to know that the data that you're looking at is is consistent in a strong consistency model, and that it's, in that sense, is the truth, that you're not looking at a product that was sold to a non-existent customer or whatever other consistency constraints need to be in place. If you look at atomicity, which is the third of the guarantees that you get from ACID, that's all about knowing what happened. Did the changes that I make all happen? Did they all not happen? When did they happen? All that stuff, that's about atomicity. Guarantees of isolation are about you and I are editing the same Microsoft Word document. I don't want you to just overwrite my version of it without having some kind of structured model around that. But all of those kind of pale into insignificance compared to the most important thing about ACID, which is transactional systems allow much simpler applications, and simpler applications are more reliable, they're cheaper, you can build them with lower skilled teams. The abstraction of ACID transactions is what allows us to build the many, many thousands of business applications that we have without having to have PhDs writing every line of code. And the same is true for database administration, that it's extremely powerful for a database administrator to be able to update all of the zip codes of all of the users in one go and know that it all happened at the same time or didn't happen. Those kinds of things, simplification of database administration, hugely powerful as well. So the answer with ACID is you definitely want it if you can have it. It guarantees your data in ways that systems without it don't guarantee your data, simplifies your applications, and in fact it also provides a sort of a recovery model in the case of disaster, which is much richer and much more powerful than systems that don't have ACID transactions. So if you look at that as a kind of an objective, you'll see that is it as important as elasticity? A lot of people don't think so, but you definitely want it if you can have it. SQL is the third piece, and sort of Eric was saying, at the end of the day, SQL is about server-side computation, and not having a server-side computational model, which, by the way, many of these so-called NoSQL systems don't, is a very big problem. It creates application complexity. It requires you to get all the data across the application side and do the equivalence of your aggregates or joins or whatever it is you want to do on the application side, which is prone to error, which makes applications much more complex, which takes them longer to build and more complex to maintain, and so on. Similarly with performance, if you've got to somehow join 300 million Americans with 20,000 towns that they live in, doing that on the client side requires you to get all the data across to the client side. So even aside from application complexity, you've also got big performance issues that are a consequence of not having server-side processing. Also reliability that comes with that, so that's fairly obvious. I think one of the things people miss with SQL is just how powerful it is. And if you ask in the context of big data and analytics, Hadoop came out and people thought that SQL was over for that kind of processing, and it turns out that there's been a massive move back to SQL. Why is that? It's because of the power of the language, largely. It's the ability to walk up to petabytes of data and to do very powerful transformations and selections and everything else directly with sort of one-line commands. SQL is extremely high-level and powerful language. But most importantly, I think it is that SQL is standardized, at least somewhat standardized, enough that there are lots of practitioners out there that know how to write SQL applications, know how to manage SQL data, know how to back it up or how to load it into warehouses or whatever they need to do. You can hire those people readily. The language is good enough to do those things. And so that's one of the reasons that we've had the kind of analytics and big data world moving back to SQL, and we're now starting to see it with operational databases like NuoDB. The last comment is a little bit more subtle, but if you're an enterprise guy, you know what I'm talking about. Enterprises don't want data to be captive to applications. They want the data to be independent of the applications because it is an asset, because you do want to be able to back it up and analyze it and audit it and ETL it and everything else, and SQL is the way that you do that because SQL is an application-independent language. So what you know about SQL is that it's basically, you need a server-side language. It should, might as well be a set-based declarative language. Definitely needs to be something which is mature and optimized and high performance. And pretty much you're describing SQL. Maybe somebody will, SQL is not very pretty. Maybe someone will come up with a better thing, but frankly, right now it's good enough. So you end up in this kind of conclusion from the original question, which is that elasticity is a kind of a necessary thing. If you can possibly have ACID, you should have it. If you possibly have SQL, you should have it. The reason that we haven't is because it's been very hard. And so people have been left with this choice of going down the track of not having data guarantees and not having powerful server-side processing models. And what we're really talking about now is the question of, can we have both? It's tough, but is it impossible? So Elastic SQL is what we're talking about. It's something which Jim and I kind of talked about when we founded the company some years back. These are some of the design objectives, and you'll see they're pretty much the things that we've been talking about. It's about, can I add nodes to a running database? Can I take nodes away from a running database? Can I get the benefits of that to include that it runs continuously, that it can handle capacity on demand, that it can do automated load balancing, and it can run in multiple data centers at the same time? Those were the goals of the system. And just to look at it from a kind of a market perspective, you'll see we're talking about on the upper layer really traditional relational database systems, very powerful as databases, more modern systems on the bottom, which are very powerful as cloud systems, but less powerful as databases, and really this kind of requirement for, can you put those two things together? That is what we've done. It's also what Google's done. So you'll note that at the bottom right here, we're talking about something called Google Cloud Spanner. Google, of course, being the sort of progenitor of NoSQL, came out in their F1 white paper. I recommend that you read that if you're interested, saying that in order to run AdWords and now multiple other applications, they couldn't do that on their NoSQL systems, and they couldn't do that on their MySQL systems, and they had to build what is in effect an Elastic SQL system. They call that system F1. It's built on technology called Spanner, and that technology is now available to you or I as a service on the Google Cloud, and it's referred to as Google Cloud Spanner, which is an Elastic SQL database. It does all the things that we've been talking about. There are others, and I would expect to see more and more people coming out with systems that are designed to deliver this combination of the elasticity, which, as I say, is a requirement, but with that, to have the power of SQL and the guarantees of ACID transactions. There's another company here called Cockroach Labs, for example, that is some of the folks from Google that started a company and brought similar technology to bear. So just a little bit of kind of technology, and I think that there's some technologists listening, so I'll dive into this a bit. How can you build one of these things? Some of the historical approaches are very limited. The most obvious one is what you call shared disk architectures. In effect, you've got a tightly coupled cluster, a bit like the old VMS clusters or the Oracle RAC clusters, IBM PureScale. These are systems where a small number of identical machines are tightly coupled on a sort of a high-speed interconnect and accessing a single sort of master data storage system. And they're okay. They definitely give you some benefits over single server systems. They're fragile. They're not what you would call elastic. You sometimes can add nodes and things, but it's a very limited kind of elasticity. And in fact, many of the biggest databases in the world are run in this way. So I don't mean to suggest that they don't work. They do. They just don't give us the elasticity we're talking about. A lot of systems, and typically kind of large internet companies, use sharded systems where you basically divide the database into multiple databases, and either the application figures out which database server to go to, or you put some kind of middleware layer over the top and try and automate either the sharding and the load balancing and and so on. Challenging this because obviously you can't really get around the issue of multi-node queries and transactions. But you also have load balancing challenges that typically these systems can end up with one or two of the nodes being maxed out and the others sitting waiting. And so you have to move data around, and it's kind of a complex thing, complex to back up, complex to manage. As my co-founder Jim would say, sharding is a great idea if you don't have any other ideas. I'd probably agree with that. The third one here is actually what Google are doing. And so this is kind of synchronous replication. It's basically two-phase commit, for those of you that are familiar with it. Two-phase commit plus, they're also using a sort of a quorum technology as well in their clusters. And this is sort of, you should think of as kind of brute force approach. They have GPS devices on every server. They have atomic clocks on every server to support something called true time, in which they use for global serialization. It's quite a heavy-duty thing, but it works, and it really does work. They're running it at an incredible scale with incredible performance. Every time you go and do a Google query and there's kind of AdWords coming up, those AdWords are going through the system. And to be clear, it is absolutely a SQL, distributed SQL database system that's at global scale. The thing that on the right-hand side is what we're doing. It's called a durable distributed cache, and it is what that says. It's basically a cache-like system which does dynamic and on-demand loading of our data objects in a cache-like way with all sorts of typical cache style management of that data. It's distributed, so there are many nodes that might have any given piece of data, and it's durable. There's some nodes that take responsibility for maintaining backing stores. And so from the outside, it supports full SQL-style database services, no different in principle from an Oracle or a SQL Server or a DB2, but it's an upside-down database system. It's really a sort of an in-memory system that happens to be maintaining transactional durability in the way I've described. Hold on a minute, just trying to get to the next slide here. A little bit more detail on this. Don't have a lot of time to go into this, but happy to talk about it in the Q&A. Basically, our nodes, which are these transaction engines and storage managers, are peer-to-peer nodes. They have specialized roles. Some of them maintain the backing stores, which is the storage managers. Some of them take client connections and run SQL transactions, which are the transaction engines. Underlying all of this, there are basically container objects, and these container objects might be your user data, like your sort of tables and so on, but they might be indexes and they might be our system data. It doesn't really matter. They're just objects being passed around the system in a container-like fashion, and in some sense, it's a container management system. The objects have actually a lot of the transactional behavior that is delegated to them in a sort of an actor pattern, so that any given object knows how to serialize itself to disk or serialize itself to the network or maintain replicas of itself in a consistent fashion. The system, I should mention, is a SQL system because layered on top of this distributed object system is a SQL engine. But we could just as well layer on top of it a JSON engine or a graph engine or anything else. So just to look at some of the systems in the market, we talked about the kind of the Google stuff ourselves. You know, when you look at the SQL capabilities, and I apologize, there's a bit of a snafu on the slide, but the SQL capabilities and the Elastic capabilities, we went to great lengths to make sure that there's a very rich SQL implementation. We've got customers out there doing thousands of interactions per transaction. We've got customers that are running 13-way joins. This is a very serious SQL engine. At the same time, it's extremely elastic, and it's a system where adding and deleting nodes is a matter of seconds. It's a very, very simple system to be able to just, in an automated fashion, start and stop nodes, add capacity, delete capacity, and so on. That kind of dynamism, we think, is the future, and it's very much part of the design of the system. In terms of customers, I'd love to go into some of these at greater depth, and maybe we'll get a chance. What I can tell you is that, for example, let's pick London Stock Exchange. You know, we went in there and they said, we're running, and I won't mention the name of the company, but they're running a traditional relational database system, hit the limits of it, have a requirement through the MiFID regulations to get to 10x that kind of performance. We rolled out 10 nodes and we hit the performance requirements instantly. That's the kind of thing that you see when you can scale out a SQL database. We're doing that all fully transactionally, and it's a full SQL engine, and we're running at 10 times the speed that they were doing on a traditional SQL database. Lots more to be said about those. So Eric, I did want to kind of make sure that we've got enough time to talk. The main kind of point I wanted to make is going back to the initial comments, which is that as a database decision maker, whether you're an application developer or a CIO or anybody else, you have in recent years been faced with this kind of choice of, do I really want to be next generation? Do I want to be cloud and containers and some microservices and so forth? Or do I need to just hang on to my trustworthy database systems that run SQL and do transactions and fit in with all of my kind of business processes and for which I can hire people relatively easily and so on? And I think what we're talking about here in terms of Elastic SQL is that those two things are coming together, that just as has happened in the analytics and big data world, there's a resurgence of SQL in the context of cloud, and these kinds of cloud-native databases are emerging and are, in fact, being successful in very large deployments worldwide.
Yeah, that's great news. And this, I'm going to push this slide here again with some of these fantastic brands. I mean, the London Stock Exchange, you want to talk about mission critical, that's some serious stuff. Can you talk about how a company would migrate to using NuoDB from a traditional system? What does that process look like of populating the database, and how long does it take? What I'm sure what you want to do is be able to run concurrently for a period of time to make sure you didn't miss anything. Like, how painful is it to migrate off of a traditional relational database if you are an organization like the London Stock Exchange?
Very good question, obviously. There's bound to be an 80-20 rule. For the vast majority of database systems, actually, we're able to move across quite quickly. We've moved DB2 application, big DB2 application in about 4 days. So it can be done very quickly. And of course, there's circumstances under which people are using some sort of exotic things that are harder to do. The steps in the process are pretty much what you said, which is that you've got to basically suck the data out of the existing database system and put it into ourselves. Our APIs are standard APIs. It's JDBC and ODBC and all those kinds of standard things. Our SQL is extremely standard ANSI SQL and quite rich. And so moving the data is relatively straightforward. And a lot of the time actually is spent more on the testing and the kind of performance characterization and so forth, rather than the work of actually moving the data or moving the workloads. But again, it's an 80-20 rule. There are always going to be some things that people will find there's some things that we do one way and somebody else does a different way, and we work our way through those.
Okay, and in terms of elasticity, let's talk about adding nodes, because you mentioned a few comments about that early on in the webcast. Let's say you get that spike of activity. It's the Christmas season, some advertisement went out early, you didn't expect that much activity, so you've got a spike in traffic. How dynamically can those nodes be provisioned, and how do you actually manage that? In other words, from a management console, do you give the system the capability to dynamically scale up X number of nodes, or is that a manual process? How does that happen?
Yeah. So let's just get back to the point that there really are sort of two tiers of these nodes. The lower tier being the guys that are maintaining backing stores, what we call storage managers. And the two tiers scale out independently of each other. Very important point, okay? There are times when you want to add more storage managers because you're wanting to partition the data in some way, or you want more redundancy, or you want to support a backup in a different data center or something like that. So you can scale out the storage manager tier independently. But the question you asked really, which is about more users and more throughput, typically that's about scaling out the in-memory tier. And these transaction engines that we referred to, they don't touch the disk. They're really only in memory. They run as basically an in-memory database. And here's what happens. You simply you can do it manually. You can have it automated. You can run it. We have demos in which we have Kubernetes just adding nodes when needed, when it detects some kind of threshold that's been crossed. And the new node comes in, it hands over some security credentials, it joins into the database, and at some point the load balancer points user connections at it because it notices that it's not doing anything. And at that point, it just starts loading data and doing things. How long does that take? The startup is milliseconds. Sometimes, depending on how much data needs to be loaded, that may be seconds. But it's not many minutes, and it's certainly not hours. A node typically, startup time is much more dominated by how long it takes to fire up an Amazon node, for example, than it is to start up the database servers. And of course, deleting them is similar. I mean, you can crash them if you want, but shutting them down, they shut down within milliseconds. So the scale out and scale in, some people do want the thing to be automated scale out, but quite often they want to have it driven by some other business driver. They know that markets are opening and there's a Forex spike at the beginning of the day. You might as well just scale up to be ready for that. And that's not something that's driven off of kind of monitoring data.
Mm-hmm. That was the other question I was going to ask you, is monitoring the system when you're talking about, especially the spikes or the peaks and the valleys. What kind of visibility does the end user have through the NuoDB platform to see where things are, to better understand, yes, we need to start adding some nodes, or we can start deleting some nodes? Well, how does that visibility occur?
Right. Well, so we're huge believers in first of all, transparency, which is, so we're publishing huge amount of stuff that people can track. And secondly, we're huge believers in integrating with kind of the systems that people are running. And so what that boils down to is providing that information to Kubernetes or Mesos or whatever it is that you're using to run your cloud or your environment, or indeed if you're just running it locally, making that information available. Now that information includes transactional throughput, it includes latency, but it also includes things like, sort of network data, it includes our object loading and ejection data, it includes lots and lots of things. And so typically what people are observing is really, for this kind of scale out and scale in, you can do it simply based on system level information, like processor kind of utilization or network utilization or something like that. But we're providing all of this information, and what we're finding is that it's not identical from customer to customer what is the right thing to observe.
Yep. Okay. Good. We have an attendee asking a question about enabling auto scaling. How would an administrator enable that kind of thing in NuoDB?
Good. So it's a good question. So the system, it does not implement an auto-scaling algorithms itself. What it does, for example, on Amazon, what we do is we hand over to the Amazon auto-scaling tools. We tell Amazon what it is, what to do when it gets a signal from us, and it goes ahead and scales out the Amazon infrastructure and fires us up. That's typically our goal, is to be integrated into whatever you're trying to do. On a single application basis, it's actually very simple. Because starting up a node is literally a Linux command or a REST interface call, and so you can simply start that up very trivially, and you can monitor what we're doing very trivially. You can do that in a shell script or a Python script or anything you want. At scale, as I say, people will be handing that over to some kind of cloud monitor or some kind of choreography system.
Mm-hmm. Okay, no, that makes sense. And I'm looking at this Elastic SQL Design Approaches slide here, and when you get to number 3, synchronous replication, I can't help but think about all the excitement around the Hadoop movement, let's say, circa 7-8 years ago. Mm-hmm. And how disruptive that was to planning going forward, and the fact that, of course, Hadoop comes built in with a replication of 3, so every time you store data, it stores in 3 different places. But that's a lot of overhead, right? And so when nodes go down, it causes some disruption, and it's just frankly not that, let's just say it's not built for speed. And I think what you guys did is you designed a solution, again, to get back to the mantra here, that would be scalable and durable. So you had to put a lot of thought into understanding how you're going to accomplish that. And I think one of the key points you made here is this 2-tier architecture, right?
Yeah. So let me sort of kind of make a couple of distinctions, because you're touching on some important topics. There's replication. Often in the database world, people refer to replication, and what they mean is what I'm going to say is post-commit replication. In other words, data gets committed somewhere, and then it gets replicated, which is not, by definition, not transactional replication. And so that is how a lot of systems work. You know, that basically you've got a database system sitting on one node or one data center, and it does a commit of whatever the transaction is, and then by monitoring the log or something, that transaction or those deltas get shifted to another database system, and it gets updated. So it's following, it's asynchronous, it's not up to date, it's not transactionally committed. The Hadoop kind of model is something similar to that, but we needn't go into that. What we've got going here is that when we talk about synchronous replication, the way to think about this is that these systems, like let's take a Google Cloud Spanner, is a system where it's got both replicas and partitions of your entire data set sitting on different nodes, and in fact different clusters with different nodes. And that when something, in order for it to be truly transactional, if I change data item A in one place, it needs to transactionally be changed in every other place at the same time before that transaction completes. So I talked about post-commit replication. This is intra-transaction replication. It's
right.
Making sure that everything is up to date before I return to the user and say that it's committed. In order to do that, fairly obviously, you need coordination between machines. In order to do that, fairly obviously, you're going to have to go across a network. And in order to do that, fairly obviously, you're operating at something like 3 or 4 orders of magnitude slower than if you're doing it on a single machine.
Right.
And so that's what the fundamental issue is with this model of kind of a synchronous replication model or two-phase commit styles of models, is that by definition, in order to get that kind of coordination between nodes, you are going to have to send messages, multiple messages, by the way, back and forth between the nodes. And that slows you down. That's called the slow pedal. And what Jim has designed in the DDC model is something which is much, much more sophisticated. It's much finer grained. It's got an optimistic sort of asynchrony about how it's updating things. And it's heavily using something that Jim invented 30 years ago, which is called multi-version concurrency control, which is, if you want to think of it as version-based concurrency as opposed to lock-based concurrency. So what Jim did here was a sort of a turbocharged version of MVCC. And when you boil all of that goof down to the detail, what it really says is NuoDB is a very low latency. It's memory, in-memory database class of latency. Although it's distributed, communications, rather than being synchronous, which is what the Google design and the two-phase commit design is, it's asynchronous, which allows it to run in multiple data centers. So, apologies for getting into the gory details of it, but it turns out that this slide that you're looking at really tells the story in a very interesting way.
Yeah, this is good stuff. We got a very good question from another attendee here, and I'm guessing the answer is yes, but I'll throw it over to you as it came in. The attendee asks, does this architecture support data warehousing / marts with real-time capabilities to mirror from OLTP systems?
Oh, wow. Okay, so yes, but with some qualifications. Let me say this, that the core architecture could be taken very far down that track. We could go down the track of building, a full-on competitor to Vertica or Greenplum or something like that, a Netezza. We haven't done that. This system is optimized today, is optimized for operational database, a general-purpose database. Think of it as Oracle for the cloud, basically. That's what it's designed for. Now, having said that, it is extremely good at something, Eric, you mentioned earlier, which is HTAP, Hybrid Transactional Analytical Processing. It's very good, in other words, for you to do analytics on your actual operational data. That doesn't mean that we're going to migrate, we're going to manage multiple schemas and star schemas and things like that. It's you're doing that analytics on the standard operational schema of the database. But why it can do it is two things. One is because whereas lock-based concurrency is something which causes readers and writers to typically trip over each other, This multi-version concurrency control that we talked about, and this is true of all MVCC databases, allows analytics to be effectively done on a snapshot while everyone else continues to mutate the database. That's part one. Part two is, and I think that your questioner kind of alluded to this, is that you can add a node in real time, have it do whatever analytics you want on the database, and then shut that node down again. And that node, and the impact of that is quite minimal, the performance impact on the rest of the system. And so for these kinds of workloads, what we call HTAP workloads, the system is extremely good at handling those kinds of workloads. But I wouldn't put us up against, the sort of traditional warehouse engines. As of today, that's not what we're trying to do.
I see. Okay, good. We got more really good questions coming in here, so let me throw this one at you. An attendee is asking, can you explain how microservices can take advantage of NuoDB in a Docker cloud architecture?
Absolutely. One of my favorite topics. So as you know, Docker and containers are fantastic. I think they're a huge breakthrough. I think we still haven't really sort of figured out how much of an impact they're going to have. But they're particularly appropriate for stateless kinds of systems, and that makes it easy, and it allows us to deploy these Docker systems in sort of arbitrarily. The issue always comes up, well, what do you do about state, and in particular around microservices, which goes a step further. What you want for state is that you're wanting something which is easily sort of dynamically relocatable, and so which is what we are. So our transaction engines, which are the in-memory systems, you can fire it up anywhere there's an IP address that's got access to the rest of the system. And so you can start those up on the same nodes as your Docker instances. Of course, we run in Docker ourselves. Dockerizing us is a natural thing. And so you get very low latency, good access, etc. Two more points. The storage element of it, recall that I said that we've got multiple storage managers with redundant storage, which is how we recommend that you run it. Obviously, you don't have to have it redundant, but we'd recommend that you have 2 or 3 separate copies of the data. You can add these nodes anytime you want. I can walk up to a running NuoDB system and say, here's an empty storage manager. It will populate itself, and it will join in, and it will be a pair of the existing ones or the pre-existing ones, which I can switch off at that point. So the system has, even at the storage layer, the ability to move the data around, and you can do that with partitions of the data as well. The last point I was going to make is just that as relates to microservices, one of the big questions people have is, how do I have, in the microservices philosophy, the idea is very independent services that are not dependent on each other in terms of kind of deployment, sort of release trains and so on, and that the interdependencies are API-based. But you also, at the same time, want that data to be somehow centralized because you're wanting to be able to do things which are kind of process-wise analytics and so forth. And so a distributed SQL database is particularly good at this, is that they can maintain their data independently at the same time that data is in the same effective logical repository, and you can do anything you want analytically. So we love the Docker environments, we love containers, we love microservices. We think that there's nothing on the planet that's as well suited to those environments as ourselves.
Okay, good. We got some more really good questions coming in here. One of the questions is pretty simple. Could you take a minute to explain HTAP? So this whole concept of hybrid, transactional, analytical database systems for processing, this kind of goes back to what we were talking about at the top of the hour. And if you would, if possible, could you kind of compare and contrast what you're doing with SAP's whole movement towards this in-memory architecture with HANA, right? Because again, they're attacking some of the same stuff, but how do you differentiate?
Yeah, absolutely. So HTAP, just to kind of make a sort of a further comment on that, a lot of HTAP is about applications that include analytics, as opposed to if you like, research analytics or batch analytics or stuff like that, which are very valuable things. But a lot of applications, and we talked earlier about AdWords, in the time that you do a Google query, AdWords, and the main query, of course, does a big index lookup to go and get you whatever your pages of links are. In parallel, AdWords rushes off and goes and does a market optimization for what ads are appropriate, which ones have been paid for, which ones are reached, which ones are within the right time boundary or geographic boundary, whatever, optimizes all that stuff, does a bunch of kind of transactional stuff on the back end, and still within the sort of half second or so of the page coming back, it displays those ads for you, right? That is an analytical undertaking. It's doing analytics, right? And that's a typical HTAP kind of a situation. There are lots of others, but that gives you a sort of a picture of the kinds of things that you're doing, and you're doing it at a gigantic scale. So HTAP is about this idea of being able to do analytics on your operational data in real time, and that data is absolutely fresh, doesn't have to be moved into some back-end system or anything else. Once again, there are circumstances under which you do want to move it into back-end systems and do all sorts of other things. That's fine. We're not trying to kind of stuff. We're just saying that for HTAP, that's what HTAP is all about.
Yeah, that's good. Yeah, go ahead.
Yeah. So, sorry. So, Eric, you had a sort of a secondary part of that question.
Yeah, well, I was just kind of asking how you compare and contrast with what SAP is doing with HANA. I mean, of course, they've got some pretty specific use cases they're building around, and I think that I'm just guessing here that you're a bit more flexible in terms of the use cases that you can empower, whereas I'm guessing HANA is, of course, focused on those heavy industrial clients, Fortune 500 companies with global presence, that kind of thing. But can you talk about that for a second?
Yeah, I mean, we know a lot about HANA. I'm not keen on talking too much about other people's technology. I think it's a very interesting approach. What they're essentially doing is saying we've got an in-memory system that's going to sit. We're going to load the entire database into memory, and we're going to have, if you like, both column-oriented storage and row-oriented storage in that system, and you can pick and choose, and we're going to be able to handle different kinds of workloads as a consequence. Our model is very different. Remember, I said that at the core of this, it's actually much more important than it sounds. At the core of this are these intelligent objects, these kind of data containers that we internally call atoms. And these data containers actually do all the work. The system doesn't, at a deep level, the system doesn't really know about the storage formats, whether it's column-oriented or row-oriented or anything else. These are just objects, and the objects are intelligent. You can tell them to do things, they do things. And so for us, topics of is it row-oriented, is it column-oriented, don't really matter. What matters is our ability to load these objects and have them efficiently maintain, consistent state across, potentially quite large clusters of machines.
Yeah, that's cool stuff. And, we talked a bit about Docker here and containers and the whole issue around stateless. And there's another component I'd like to throw into that conversation, which is application design, because what we're seeing here is the foundation shifting and becoming more flexible, frankly, and that changes how application developers think about what they create, right? Can you kind of talk about how developers need to start rethinking the architecture of the foundation as being more nimble, as being more flexible, and how that changes the way they design applications?
Yeah, although maybe I'm going to say something slightly different from what you might expect. And my analogy is we've got a requirement for a new type of train service, and there's an existing set of railway lines out there. One approach is to say, let's rip up all the railway lines and relay them so we can deliver the new kind of service. And a different approach is to say, well, can't we design a smarter train to run on the existing infrastructure? And in this sense, the existing infrastructure is SQL and transactions. And we're saying, you already know how to build those applications. You've got the tool sets, you've got the ecosystem, you've got your standard business practices, you've got your training, you've got, everybody, you've got your backup strategies. That's the railway line, that's the infrastructure. And our job is to make it so that you don't really have to do anything differently. So let me give you some concrete examples. From our perspective, it's JDBC. That's the same thing you use to talk to Oracle, right? It's a single logical database. Even though you've got all these kinds of funny things going on under the covers and objects being loaded and sort of however many nodes involved and things dynamically moving around, at the end of the day, the application developer simply sees a traditional single logical database. It's got some tables and it's got some rows and it's got some indexes and the rest of it, and you don't see all that stuff going on under the covers. And that's part of our point. What we want is for application developers to be able to hand over all of that operational decision-making about performance and about which machines it's running on today and all of that is somebody else's challenge. It doesn't come into the application developer's mindset. They are simply building a SQL application, period.
Okay, good. We got a couple more good questions. I'll throw one over to you, and then I'll give you a very technical question that came in. You talk about migrating systems, right? So this is always one of the big questions for a vendor such as yourself. Are you going to go out and find net new business, meaning net new use cases, or are you going to be used to supplant existing technologies? And it seems to me we're going to see a good bit of both those categories moving forward, simply as companies recognize that the foundation is changing and that if they want to remain nimble and agile, and I think that's going to be a hallmark of success going forward, they need to have a more robust infrastructure underneath them. But you've got one of these lines here in your matrix, migrate existing SQL applications. Well, that's something that you really have to think about if you're going to move over, and you handle that. Can you kind of talk about why you're able to facilitate in that specific use case? Because I'm guessing that would usually be one of the red flags that users are going to throw up is, hey, I don't want to change the app I'm using.
Yeah. Well, and there are a couple of questions in there, so let me sort of take it quickly. First of all, we've got a mix of people that are building new applications and people that are moving existing applications. There are many existing applications that people are just going to put on the cloud, running on a single server traditional database system, and they're fine with it. And that's fine with us. But there are many applications, they're often strategic applications, where people really need the elasticity. Either that's about performance, or it's about uptime, or it's about kind of cloud enablement or something. And so we do both, and we're very happy to do both. What we'd say is that, why is that check mark there? The answer is that you've got to have rich SQL support to do this. The kinds of things people are doing with our system, both in terms of kind of the SQL capabilities and in terms of performance, in some cases are quite extreme. They put us up against traditional relational databases and they say, we want to see you on similar hardware being at least as fast, and then we want to add more hardware and see you go much faster. So, stuff like that. The reason that there are not check marks, for example, if you look at Google's offering, their SQL is not pure SQL. It's not rich SQL. It's in fact, the way that you write things to their database, the recommended way is to not use SQL at all. And we're pure SQL. We're pure ANSI SQL, and we're rich ANSI SQL, and that's what people need. We also have things which people think of as more exotic capabilities, including triggers and stored procedures and other things that are sort of deeper in the sort of SQL stack. But that's what that's all about. And yes, we're very happy. Many of our biggest customers have not only moved applications, but we've got big customers that have literally bet the farm on us. We're talking about multi-billion-dollar companies that have simply said, we're ripping out existing SQL solutions and we're replacing you across the board.
Yeah, that's the kind of evidence you're looking for when you're out there talking to prospects, right? When you've got those major league industrial use cases and you've stepped in and hit home runs. That's what people want to hear. Here's a very good technical question, and I'm curious to know the answer myself. The question is, if you replicate data in memory on demand, isn't that the same as synchronous replication? Can you kind of talk about that for a second?
Wow, it's going to take longer than a second. There's a patent on this, and you're very welcome to go and read it if you understand patentese. The answer is no. The answer is that would require us to do essentially what Google's doing, which is to have synchronous replication between them. I would remind you that under the covers, and apologies to people that are not as technical, but under the covers, what's going on is it's a transactional system. And so if you think about the messages that are going between these nodes, a transaction gets started, a whole lot of mutations happen, they get essentially published around and subscribed to, and then at some point there's the end of that transaction, which takes the form of either a rollback or a commit. And that allows us to, that window of different things happening allows us to do all sorts of interesting things. So I don't have time to go into it right now, but no, we are not effectively trying to maintain a distributed shared memory grid, which is synchronously replicated. That would be that would require much tighter coupling. The system is close to 100% asynchronous because of what I just said. But Eric, it's a much longer conversation, and we're very happy to talk to people about how that works.
Okay, that sounds great. Well, let's see, folks. We burned through an hour and some change here. I think there was one more question lingering in the back of my mind. And it doesn't come to me at the moment. But, yeah, this is just fascinating stuff. I guess one question I'd throw out to is cloud infrastructure, right? So you've mentioned Amazon Web Services, of course. Azure is out there. There's a relatively new company that we've actually been talking to called Wasabi, which is promising to be something like 5 times faster than AWS and 20% the cost. As those new offerings come down the pike, I'm guessing that you guys are, again, pretty well suited to leverage that sort of thing, right? I mean, I always worry a little bit about the dominance of Amazon Web Services and the irony of Microsoft saving the day. I think we're going to see some more players step into that market for purpose-built type solutions. But you guys don't care, right?
Yeah, I mean, we're cloud independent. We've gone to great lengths to make sure that we don't make assumptions about specialized hardware of any sort. So we're running on commodity hardware, be it machines or networking or anything else. I would remind you that our ability to run in multiple data centers simultaneously also includes, naturally, the ability to run in multiple clouds simultaneously. So if you chose to, you could run some of our nodes on AWS and some of them on Wasabi and in the same database at the same time.
Mm-hmm. That's good stuff. And, one of the things that the Wasabi folks talk about is that they're kind of throwing down the gauntlet on standardizing APIs. So what they've done is they've mimicked the Amazon Web Services API such that you could just shift everything over from one place to the next. Do you see that as a potential standard coming down the pike, establishing some standards around APIs for cloud storage?
I suppose our view on it is that there's obviously some kind of de facto standards happening at various levels of the stack, and that's fine. But for the most part, we keep out of the kind of cloud war stuff. And so we happily run on AWS, we happily run on Azure, we'll happily run on Google. I don't know that we've tried running on Wasabi, we've certainly run on IBM's soft layer. And we just simply try to keep out of that. A lot of our customers are wanting cloud independence. One of the reasons that they would choose us is so that they can decide on Monday morning to move to a different cloud, or in some cases run on one cloud in Europe and another in the US for whatever reasons. That's the sort of customers that that we're dealing with.
Well, that's great stuff, folks. Thanks for some fantastic questions out there for our attendee friends. We do archive all these webcasts for later viewing. Feel free to share it with your friends and colleagues. And a big thanks to Barry Morris and his team over at NuoDB for sponsoring our webcast, our database research this year. Good stuff. Things are changing. There are lots of options out there. And like you say, Barry, I love the whole capacity to move from one environment to another. Nobody wants lock-in these days. With that, we're going to bid you farewell. Thanks again, folks. We'll talk to you tomorrow at 1 Eastern for our new series, Now Streaming. Don't miss that. My good buddy Damian Black is going to be back in the hot seat, building an application in minutes for IoT analytics. Talk to you then. Take care, folks. Bye-bye.
Thanks. Bye-bye.